Tonight, we're going to answer a question that sounds straightforward, but turns out to be one of the most fascinating puzzles in all of astronomy. What actually lies beyond the edge of the solar system? You probably picture it clearly in your mind. 8 planets orbiting the sun, and then after Neptune, nothing. Just empty space. But here's what most people never realize. The solar system doesn't end where you think it does. In fact, it doesn't really end at all, not in one clean line. Beyond the familiar planets lies a vast, layered wilderness of frozen worlds, invisible boundaries, and a cloud of debris so enormous it stretches nearly halfway to the next star. And by the end of this journey, you'll never think about the edge of our solar system the same way again. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. If someone asked you to draw the solar system right now, you probably do what almost everyone does. You draw a circle with the sun in the middle, then 8 smaller circles around it representing the planets. Mercury close in, then Venus, Earth, Mars, then the bigger ones, Jupiter, Saturn, Uranus, and Neptune on the outside. Maybe you'd add a few rings around Saturn. Maybe you'd even throw in a little dot for Pluto somewhere out past Neptune. And then you'd stop. You'd put your pen down. Because in your mind, that's where the solar system ends. After the last planet, there's nothing. Just black, empty space stretching out to the stars. And honestly, that's exactly what most of us were taught. Every textbook, every classroom poster, every diagram you've ever seen reinforces the same picture. A neat, orderly collection of planets orbiting the sun with clean boundaries and a clear edge. The sun is in the center. The planets go around it. And beyond the outermost planet, there's a kind of cosmic wall where our solar system stops and the rest of the universe begins. It's tidy. It's simple. And it's deeply, fundamentally wrong. The solar system doesn't end at Neptune. It doesn't end at Pluto. It doesn't end at any single place you could point to on a map and say, here, this is the line. On this side is our solar system, and on the other side is everything else. The reality is far more complex, far more interesting, and far more enormous than the simple planetary picture suggests. But to understand why, we first need to understand why the simple picture exists in the first place, and why it's so hard to let go of. The reason most people think the solar system ends at the planets comes down to something very human. We like edges, we like boundaries, we like knowing where one thing ends and another begins. It's how our brains work. When you look at a table, you see where the table ends and the floor begins. When you look at a country on a map, you see borders, clean lines separating one nation from the next. Our minds crave these boundaries because they help us make sense of the world. Without them, everything blurs together and becomes confusing. So when we think about the solar system, we instinctively look for an edge. And the most obvious edge is the outermost planet. After all, the planets are the most visible, most dramatic objects in the solar system after the sun itself. They're what we've studied the most. They're what we've sent spacecraft to. They're what we've named, categorized, photographed, and mapped in extraordinary detail. The planets feel like the solar system. And if the planets are the solar system, then the edge of the planets must be the edge of the solar system. Right? This intuition is reinforced by how we teach astronomy. Think about every diagram of the solar system you've ever seen. The planets are always shown relatively close together, orbiting the Sun in neat concentric circles. Sometimes the diagram includes the asteroid belt between Mars and Jupiter. Sometimes it shows the orbits to scale. But almost always the diagram ends at Neptune or maybe Pluto. Beyond that last orbit, there's just empty black space. Nothing. The diagram literally runs out of things to show. And since the diagram is how most people visualize the solar system, their mental model of the solar system also runs out of things at that point. But here's the problem with those diagrams. They're not wrong exactly, but they're deeply misleading. They show the planetary region of the solar system, which is real and important, but they leave out everything beyond it. And what's beyond it is enormous. So enormous that the entire planetary region, everything from Mercury out to Neptune, is just the innermost core of a structure that extends hundreds or even thousands of times farther. Imagine you're looking at a map of a city. The map shows the downtown area in detail. Every street, every building, every park. But the map just stops at the edge of downtown. Beyond that edge, the page is blank. You might look at that map and think, okay, so the city ends here. But the city doesn't end there. There are suburbs, industrial zones, farmland, and then countryside stretching out for miles and miles in every direction. The map just didn't show them. That's essentially what's happened with our understanding of the solar system. The standard picture shows the downtown, the planets, and leaves everything else blank. But the suburbs extend far, far beyond what the map reveals. Let's talk about scale for a moment, because understanding the distances involved is essential to understanding why the simple picture is so incomplete. We measure distances in the solar system using a unit called the astronomical unit, or AU. 1 AU is the average distance from Earth to the Sun, about 93 million miles or 150 million kilometers. This is a useful measuring stick because it gives us a sense of how far things are relative to something we understand. The distance from our planet to our star. Mercury orbits the Sun at about 0.4 astronomical units. Venus is about 0.7 astronomical units out. Earth is at 1 astronomical unit by definition. Mars is at about 1.5 astronomical units. These inner rocky planets are all relatively close to the Sun, packed within a region less than 2 astronomical units across. Then there's a gap, the asteroid belt, and we reach the gas giants. Jupiter orbits at about 5.2 astronomical units. Saturn is at about 9.5 astronomical units. Uranus at about 19.2 astronomical units. And Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. 30 astronomical units. That's the distance to Neptune. 30 times the distance from Earth to the Sun. That's about 2,800,000,000 miles. It's a genuinely enormous distance. Light from the Sun takes about 4 hours to reach Neptune. When the Voyager 2 spacecraft flew past Neptune in 1989, it had been traveling for 12 years to get there. 12 years of constant flight through the vacuum of space at tens of thousands of miles per hour just to reach the outermost planet. That's how far away Neptune is. And for most people, that's where the solar system ends. But here's what most people don't realize. 30 astronomical units is nothing compared to the true extent of the solar system. The actual structures beyond Neptune extend not to 50 astronomical units, or 100 astronomical units, but to tens of thousands, even 100,000 astronomical units from the Sun. The planetary region that we think of as the entire solar system occupies less than 1/10 of 1% of the solar system's total volume. Less than 1/10 of 1%. Everything you've ever seen in a diagram of the solar system, every planet, every moon, every asteroid, all of it fits inside a tiny bubble at the very center of a structure that's thousands of times larger. To put this in perspective, if the entire solar system out to its farthest reaches were the size of a football field, the region containing all 8 planets would be smaller than a quarter resting on the goal line. That's how small the planetary region is compared to the full solar system. When you look at a diagram that shows the planets and nothing else, you're looking at that grain of sand and assuming it's the whole field. The reason the full solar system is so much larger than the planetary region has to do with how the solar system formed and what got left behind in the outer reaches. To understand this, we need to go back about 4.6 billion years to the birth of the Sun and everything around it. The solar system formed from a giant cloud of gas and dust called a solar nebula. This cloud was mostly hydrogen and helium, the simplest elements, but it also contained heavier elements like carbon, nitrogen, oxygen, silicon, and iron. These heavier elements had been produced by earlier generations of stars that lived and died before our Sun was born, scattering their processed material into space through supernova explosions and stellar winds. About 4.6 billion years ago, something disturbed this cloud. Maybe a shockwave from a nearby supernova. Maybe a gravitational perturbation from a passing star. Whatever the cause, parts of the cloud began to collapse under their own gravity. As the cloud collapsed, it began to spin, flattening into a rotating disk with a dense, hot center. That center became the Sun. The disk of material around it became the raw material for everything else. Planets, moons, asteroids, and comets. In the inner part of the disk, close to the young Sun, temperatures were high. Only materials with high melting points could survive. Metals and rocky minerals like silicates. These materials clumped together through collisions, gradually building up into larger and larger bodies. First dust grains, then pebbles, then boulders, then objects miles across called planetesimals, and eventually the rocky planets we know today: Mercury, Venus, Earth, and Mars. This region was too hot for volatile substances like water ice, methane, and ammonia to remain solid. So the inner planets ended up being made mostly of rock and metal. Farther out from the Sun, beyond a boundary called the frost line or snow line located at roughly 3 to 5 astronomical units from the Sun, temperatures were cold enough for these volatile substances to freeze into solid ice. This was critical because it meant there was much more solid material available to build planets in the outer solar system. Not just rock and metal, but ice as well. The abundance of solid material allowed the cores of the outer planets to grow much larger. Once these cores reached a critical mass, roughly 10 to 15 times the mass of Earth, their gravity became strong enough to pull in enormous amounts of hydrogen and helium gas directly from the surrounding disk. This is how Jupiter and Saturn became gas giants, massive worlds with small rocky cores surrounded by thick envelopes of gas thousands of miles deep. Uranus and Neptune formed in a similar way but captured less gas, making them ice giants rather than true gas giants. But here's what matters for our story. The planets didn't use up all the material in the disk. Not even close. In the inner solar system, the leftover rocky debris became the asteroids. In the outer solar system, leftover icy debris became something else entirely. And there was a lot of it. Beyond Neptune's orbit, vast quantities of icy material remained. Small frozen bodies, mixtures of water ice, frozen methane, frozen ammonia, and rock that never managed to accrete into a full-sized planet. Why not? Partly because the material was spread over such enormous volumes that collisions were rare. Partly because the gravitational influence of Neptune and the other giant planets stirred up the orbits of these small bodies, preventing them from settling into the kind of calm, circular orbits that would allow them to gently merge and grow. And partly because the density of material out there was simply too low. There wasn't enough stuff in any one place to build a planet. So instead of forming a planet, this material remained scattered across an immense region of space beyond Neptune. Trillions of small frozen bodies orbiting the sun in the cold darkness far from its warmth. A vast population we would not begin to discover for decades. Some of these objects settled into relatively stable orbits just beyond Neptune. Others were flung onto wild, elongated paths that carried them far out into space before swinging back. And still others were kicked so far from the sun that they ended up in a vast, loosely bound shell surrounding the entire solar system at distances so great that the sun appears as just another star in their sky. These leftover icy bodies are the key to understanding why the solar system is so much larger than the planetary region. The planets formed in a relatively compact zone close to the sun, but the debris, the material that didn't become planets, got scattered across a volume of space that dwarfs the planetary zone by a factor of thousands. This debris is still out there. It's been orbiting the sun for 4.6 billion years, cold and dark and almost impossible to see. But it's real, and it extends the solar system far beyond anything the simple planetary picture suggests. The first hint that there was something substantial beyond the planets came long before anyone directly observed it. It came from comets. People have been watching comets for thousands of years. Ancient civilizations saw them as omens, signs of coming disaster or divine displeasure. The appearance of a bright comet in the sky was an event of enormous significance, recorded in chronicles and carved into monuments. But it wasn't until the scientific revolution that people began to understand what comets actually were. In 1687, Isaac Newton showed that comets follow the same laws of gravity as planets. His friend Edmund Halley used Newton's methods to calculate the orbit of a bright comet he observed in 1682 and predicted it would return about 76 years later. When the comet reappeared in 1758, right on schedule, it confirmed that comets were members of the solar system, objects orbiting the sun on long, elongated paths that carried them far from the sun and then brought them back. But this raised a question. Where did comets come from? Their orbits showed that they spent most of their time far from the sun, in the outer reaches of the solar system, only becoming visible when they swung close enough for the sun's heat to vaporize their ices and create the glowing tails we see from Earth. Some comets had relatively short orbital periods of a few years or decades, suggesting they didn't venture too far from the Sun. But others had orbital periods of thousands or even millions of years, suggesting they came from incredibly distant regions of space. In 1950, a Dutch astronomer named Jan Oort studied the orbits of these long-period comets and made a remarkable deduction. Based on their orbital characteristics, he concluded that there must be a vast reservoir of icy bodies surrounding the solar system at distances of tens of thousands of astronomical units from the Sun. These objects would orbit so slowly and be so far away that they'd be essentially invisible, but occasionally, the gravitational influence of a passing star or the gentle tidal pull of the Milky Way galaxy itself would nudge one of these distant objects, altering its orbit and sending it falling inward toward the Sun. As it approached the inner solar system, the Sun's heat would vaporize its ices, creating a visible comet. We'd watch it streak across our sky, marvel at its beauty, and then it would swing back out into the darkness, returning to the distant reservoir from which it came. Oort's hypothesis meant the solar system was far larger than anyone had imagined. Not just 30 AU across, the distance to Neptune, but perhaps 200,000 AU across. A vast sphere of icy debris surrounding the planetary system, like a cosmic cocoon. This was a radical idea in 1950. The solar system wasn't a compact collection of planets. It was an enormous structure with a tiny planetary core surrounded by a huge shell of frozen leftovers from its formation. But the outer reaches weren't the only unexplored region. Even before Oort's proposal, an Irish-born astronomer named Kenneth Edgeworth had suggested in the 1940s that a belt of icy objects should exist just beyond Neptune's orbit. In 1951, the Dutch-American astronomer Gerard Kuiper explored a similar idea independently. Their reasoning was straightforward. If the solar nebula extended beyond Neptune, and there was no reason to think it didn't, then there should be leftover debris in that region, just as the asteroid belt represents leftover debris between Mars and Jupiter. The material beyond Neptune would be icy rather than rocky because of the cold temperatures, but it should be there. This prediction sat largely untested for decades because the technology to detect these small, faint, distant objects simply didn't exist. These hypothetical icy bodies would be tiny compared to planets, perhaps a few hundred miles across at most, and they'd be billions of miles away. They'd reflect almost no sunlight. Find them would be like trying to spot a lump of coal floating in a dark ocean, thousands of miles away. It wasn't until 1992 that astronomers David Jewett and Jane Liu, after 5 years of painstaking searching, discovered the first object beyond Neptune and Pluto. It was designated 1992 QB1, a small icy body roughly 100 miles across orbiting the Sun at about 44 astronomical units. This single discovery confirmed what Edgeworth and Kuiper had predicted decades earlier. There was indeed a belt of icy objects beyond Neptune, and once astronomers knew where to look and had the technology to find them, the discoveries came flooding in. Within a few years, dozens of objects were found, then hundreds, then thousands. Today, we know of over 2,000 objects in this region, and astronomers estimate the total population numbers in the hundreds of thousands for objects larger than about 60 miles across, with potentially trillions of smaller bodies. This was a revolution in our understanding of the solar system. The neat picture of 8 planets and then nothing was shattered. Beyond Neptune lay an entire population of worlds that we hadn't known about. A vast ring of frozen debris that extended the solar system well beyond the last planet. Pluto, which had been considered the lonely outpost at the edge of the solar system since its discovery in 1930 by Clyde Tombaugh, turned out to be just one member of a much larger population. It wasn't a lonely sentinel at the edge. It was one of the biggest objects in a crowded neighborhood that we simply hadn't been able to see before. This discovery changed everything we thought we knew about the outer solar system. Pluto, which had been considered the lonely outpost at the frontier since 1930, was suddenly just one object among thousands. And as more objects were found, some rivaling Pluto in size, astronomers were forced to ask a question that would ignite one of the most heated debates in modern science. What exactly counts as a planet? That story and the discovery that triggered it comes shortly. But the deeper point is this: the space beyond Neptune was not empty. It was teeming with frozen worlds we simply hadn't been able to see before. But here's the crucial point. Even after the discovery of this belt of icy objects beyond Neptune, even after the discovery of hundreds of frozen worlds in the outer solar system, we had only scratched the surface of what lies beyond the planets. The belt of objects just beyond Neptune is just the beginning. It's the closest and most easily detected structure in a series of regions that extend farther and farther from the Sun, each one larger and more diffuse than the last. Beyond this belt lies a scattered population of objects on wild orbits. Beyond that lies the boundary where the Sun's outflowing particles meet the gas between the stars. And beyond that lies an almost inconceivably vast cloud of icy bodies that stretches nearly halfway to the next star. The solar system doesn't end at a line. It fades, it transitions, it thins out gradually through multiple layers, each defined by a different physical process. One layer is defined by the orbits of the planets. Another is defined by the distribution of icy debris. Another is defined by the reach of the solar wind. And the outermost is defined by the Sun's gravitational influence. Each of these layers represents a different kind of edge, and none of them is the edge. They're all real boundaries, all physically meaningful, and they all occur at vastly different distances from the Sun. The planetary edge is at about 30 astronomical units. The debris field extends to perhaps 1,000 astronomical units or more. The solar wind boundary is at roughly 100 to 120 astronomical units. And the gravitational boundary extends to about 100,000 astronomical units, nearly 2 light years from the Sun. When someone asks, where does the solar system end? The honest answer is, it depends on what you mean by end. If you mean where the planets stop, that's Neptune at 30 astronomical units. If you mean where the Sun's particle output gives way to interstellar particles, that's around 100 astronomical units. If you mean where the last icy debris orbits, that might be 100,000 astronomical units. Each answer is correct, and each gives a dramatically different picture of the solar system's size. This is what makes the question so fascinating. The solar system isn't a thing with a clean boundary. It's a gradient, a transition, a slow fade from the warmth and activity of the interplanetary system to the cold, dark emptiness of interstellar space. And each layer in this transition reveals something different about how our solar system works, how it formed, and how it interacts with the galaxy around it. So as we move outward from the familiar planets, we're going to explore each of these layers in turn. We're going to visit the frozen belt of icy worlds just beyond Neptune, a region teeming with small bodies left over from the solar system's birth. We're going to follow the solar wind as it rushes outward from the sun at 1,000,000 miles per hour and slams into the gas between the stars, creating an invisible bubble that surrounds everything we know. We're going to venture into the most distant reaches, where the sun's gravity barely holds on to trillions of icy fragments in a vast, spherical cloud that no telescope has ever directly seen. And we're going to discover that the question, where does the solar system end, doesn't have one answer. It has many, and each answer reveals a different truth about the enormous, complex, layered structure we call home. The planets are just the beginning. What lies beyond them is stranger, larger, and more fascinating than most people have ever imagined. And we're about to go there. So we've established that the planets are not the edge of the solar system. They're just the innermost region, the dense, busy core of a structure that extends far, far beyond. Now, let's actually go there. Let's travel past Neptune and see what's waiting in the cold darkness beyond the last planet. The first major structure you encounter when you leave the planetary region is a vast ring of icy objects orbiting the Sun beyond Neptune. This region is called the Kuiper Belt, named after Gerard Kuiper, one of the astronomers who predicted its existence decades before it was confirmed. The Kuiper Belt stretches from roughly 30 astronomical units, right around Neptune's orbit, out to about 50 astronomical units from the Sun. That might sound like a modest distance, just 20 astronomical units of depth. But remember that 1 astronomical unit is 93 million miles. 20 astronomical units is roughly 1,860,000,000 miles. The Kuiper Belt is a ring of space nearly 2 billion miles wide, and it's filled with objects that most people have never heard of. What kinds of objects are we talking about? Icy bodies, small worlds made of frozen water, frozen methane, frozen ammonia, and rock. They range in size from chunks no bigger than a house to dwarf planets hundreds of miles across. Most of them are small, just a few miles or tens of miles in diameter. But some are genuinely substantial worlds with surfaces, atmospheres, moons, and geological histories of their own. These are the leftovers of planet formation, the building materials that never managed to assemble into a full-sized planet because the material out here was too thinly spread and the orbital dynamics too chaotic for the gentle process of accretion to run to completion. The Kuiper Belt is sometimes compared to the asteroid belt between Mars and Jupiter, and there are similarities. Both are regions filled with small bodies left over from the solar system's formation. Both contain objects that range from tiny fragments to dwarf planet-sized worlds. Both occupy a zone between planetary orbits where a planet might have formed, but didn't. But the comparison also breaks down in important ways. The Kuiper Belt is far larger than the asteroid belt. It is much more massive, containing perhaps 20 to 200 times more total mass, and its objects are fundamentally different in composition. Asteroid belt objects are mostly rock and metal because they formed in the warm inner solar system where ices couldn't survive. Kuiper Belt objects are mostly ice because they formed in the frigid outer solar system where temperatures are so low that volatile substances like water and methane freeze solid. The temperatures out here are staggering, At 30 to 50 astronomical units from the Sun, temperatures hover around minus 220 degrees Celsius, or roughly minus 360 degrees Fahrenheit. The Sun, which dominates the sky from Earth and provides all our warmth and light, appears from the Kuiper Belt as just a very bright star, bright enough to cast faint shadows, perhaps, but not warm enough to melt anything, not warm enough to sustain liquid water, not warm enough to do much of anything at all. Objects in the Kuiper Belt have been frozen solid for 4.6 billion years, essentially unchanged since the solar system formed. They're pristine samples of the original material from which the planets were built, preserved in a cosmic deep freeze at the edge of the planetary system. The most famous Kuiper Belt object is, of course, Pluto. For 76 years, from its discovery in 1930 to its reclassification in 2006, Pluto was considered the 9th planet. It was the edge of the solar system, the last outpost, the lonely sentinel standing guard at the frontier. But the discovery of the Kuiper Belt revealed that Pluto was not alone. It was just the first and most easily detected member of a vast population. Pluto is large for a Kuiper Belt object, with a diameter of about 1,473 miles. But it's not unique. There are other objects out there that rival it in size. In 2005, astronomer Mike Brown and his team at the California Institute of Technology announced the discovery of an object that would change everything. They found Eris, an icy body orbiting the Sun at a distance that varied between about 38 and 98 astronomical units. Eris was initially thought to be larger than Pluto, though later measurements from NASA's New Horizons mission revised Pluto's size slightly upward, making the two roughly comparable in diameter. But critically, Eris turned out to be about 27% more massive than Pluto. Here was an object beyond Neptune that was more massive than the supposed 9th planet. If Pluto was a planet, then surely Eris had to be a planet too. And if Eris was a planet, then what about the other larger objects being discovered in the same region? This is what forced the International Astronomical Union to act. In 2006, they established a formal definition of a planet for the first time. To qualify as a planet, an object had to orbit the Sun, had to be massive enough for its own gravity to pull it into a roughly spherical shape, and crucially, it had to have cleared the neighborhood around its orbit of other debris. Pluto met the first two criteria, but not the third. Its orbit is shared with thousands of other Kuiper Belt objects. It hasn't gravitationally dominated its region of space the way Earth or Jupiter have dominated theirs. So Pluto was reclassified as a dwarf planet, along with Eris and several other large Kuiper Belt objects. The reclassification was controversial, and it remains a sore point for many people. But scientifically, it made sense. The discovery of the Kuiper Belt showed that Pluto was not a special object sitting at the edge of the solar system. It was one member of a population. A big member, yes. An important and fascinating member, absolutely. But one member among many. The edge of the solar system didn't stop at Pluto. It didn't stop at all. It just kept going. Beyond Pluto and Eris, several other large Kuiper Belt objects have been discovered and classified as dwarf planets. Makemake, discovered in 2005, has a diameter of about 890 miles. It's covered in frozen methane and ethane, giving it a reddish-brown surface. Haumea, also discovered in 2005, is one of the strangest objects in the solar system. It is dramatically elongated, stretched into an oblong shape roughly twice as long on its longest axis as its shortest. Because it rotates extremely fast, completing one rotation in just under 4 hours. That rapid spin has stretched it out along its equator. Haumea also has a ring system, one of only a handful of small bodies in the solar system known to have rings, and it has 2 small moons. These dwarf planets are just the tip of the iceberg. For every large Kuiper Belt object we found, there are thousands of smaller ones we haven't. The Kuiper Belt is estimated to contain hundreds of thousands of objects, larger than about 60 miles in diameter, and potentially trillions of smaller bodies down to the size of pebbles. The total mass of the Kuiper Belt is estimated to be somewhere between 1/10 and 1% of Earth's mass. That might sound like very little, but spread across a ring billions of miles wide, it represents an enormous amount of material. Despite all these objects, the Kuiper Belt is mostly empty space. If you flew a spacecraft through it, you almost certainly wouldn't see anything with the naked eye. The distances between individual Kuiper Belt objects are enormous. Even though there are hundreds of thousands of large objects out there, the volume of space they occupy is so vast that the average distance between them is millions of miles. You could fly through the Kuiper Belt for years and never pass close to a single object. It's a bit like the asteroid belt in that respect. Movies and science fiction depict these regions as dense fields of tumbling rocks, but the reality is that they're almost entirely empty. The objects are there, but they're so spread out that you'd never know it from a spacecraft window. In 2006, NASA launched the New Horizons spacecraft on a mission to Pluto. It was the fastest spacecraft ever launched from Earth at the time, leaving our planet at a speed of about 36,000 miles per hour. Even at that tremendous speed, it took New Horizons 9.5 years to reach Pluto. 9.5 years of flying through empty space, crossing the orbits of Mars, Jupiter, Saturn, Uranus, and Neptune, before finally arriving at the dwarf planet in July of 2015. What New Horizons found at Pluto stunned scientists and the public alike. Far from being a dead, frozen, featureless ball of ice, Pluto turned out to be a complex and geologically active world. Its surface showed enormous variety, from vast plains of frozen nitrogen to towering mountains of water ice rising more than 11,000 feet above the surface. There were glaciers flowing across the landscape, not glaciers of water like on Earth, but glaciers of frozen nitrogen, slowly creeping across Pluto's surface under the influence of its weak gravity. The most striking feature was a huge heart-shaped region on Pluto's surface, informally called the Heart, and later officially named Tombor Regio, after Clyde Tombaugh, who discovered Pluto in 1930. The left lobe of the heart, called Sputnik Planitia, turned out to be a vast basin filled with frozen nitrogen, carbon monoxide, and methane ices. This basin is about 620 miles across and remarkably smooth, with almost no craters, suggesting it has been resurfaced relatively recently in geological terms. Convection cells in the nitrogen ice slowly churn the surface, erasing craters and creating a pattern of irregular polygonal shapes, tens of miles across. Pluto also has a thin atmosphere, mostly nitrogen with traces of methane and carbon monoxide, that extends far above its surface. This atmosphere is extremely tenuous, with a surface pressure about 100,000 times lower than Earth's, but it's real. Hazes in Pluto's atmosphere scatter sunlight, creating a blue sky when viewed from certain angles. The New Horizons images showed these hazes beautifully. Layers of atmospheric particles illuminated by the distant sun hanging above a frozen landscape of extraordinary complexity. Pluto's largest moon, Charon, was equally surprising. Charon is about 753 miles in diameter, roughly half the size of Pluto, making it the largest moon relative to its parent body in the solar system. Pluto and Charon are sometimes called a binary system because they orbit a point in space between them, rather than Charon simply orbiting Pluto. Charon has a dark reddish cap at its north pole, which scientists believe is formed by methane gas escaping from Pluto's atmosphere, drifting over to Charon, freezing onto the cold polar surface, and then being chemically altered by ultraviolet radiation from the sun into darker compounds called tholins. After its flyby of Pluto, New Horizons continued deeper into the Kuiper Belt. In January of 2019, it flew past a small Kuiper Belt object called Arrokoth, formerly known as Ultima Thule. Arrokoth is about 22 miles long and shaped like a flattened snowman. Two roughly spherical lobes joined together at a narrow neck. Scientists believe this shape formed when two separate objects in the early solar system gently collided and stuck together at very low speed, perhaps no faster than walking pace. Arrokoth is one of the most primitive objects ever visited by a spacecraft. It has been orbiting quietly in the cold darkness of the Kuiper Belt since the solar system first took shape, effectively a time capsule from the earliest era of planet formation. Studying it is like examining a fossil from the birth of the solar system. Arrokoth's surface is remarkably uniform. It's covered in a reddish material, likely organic compounds called tholins, formed when ultraviolet light from the sun and cosmic rays interact with simple ices like methane and nitrogen over billions of years. There are very few craters suggesting the Kuiper Belt at Arrokoth's distance is relatively sparsely populated. Objects out here simply don't collide with each other very often because the distances between them are so vast, and their relative velocities are so low. These visits to Pluto and Arrokoth gave us our first direct looks at Kuiper Belt objects, and they revealed a region of the solar system far more interesting and complex than anyone had expected. But the Kuiper Belt, as extensive as it is not the end of the story. Beyond the classical Kuiper Belt, which has a fairly well-defined outer edge at about 50 astronomical units, there's another population of objects that extends much farther from the Sun. This population is called the scattered disk, and it represents some of the most extreme orbits in the solar system. Scattered disk objects are icy bodies, similar in composition to Kuiper Belt objects, but with wildly elongated orbits that carry them far beyond the classical Kuiper Belt's boundaries. While a typical Kuiper Belt object might orbit the Sun in a roughly circular path at 30 to 50 astronomical units, a scattered disk object might have an orbit that takes it from 35 astronomical units at its closest approach to the Sun all the way out to hundreds or even thousands of astronomical units at its farthest point. These extreme orbits are thought to be the result of gravitational encounters with Neptune. At some point in the past, these objects passed close enough to Neptune for the giant planet's gravity to fling them onto their current, elongated paths. They were scattered, literally tossed outward by Neptune's gravitational influence, hence the name scattered disk. Eris, the dwarf planet whose discovery triggered Pluto's reclassification, is actually a scattered disk object, rather than a classical Kuiper Belt object. Its orbit is highly elongated, ranging from about 38 astronomical units at its closest to about 98 astronomical units at its farthest. At its most distant point, Eris is more than 3 times farther from the Sun than Pluto ever gets. It takes Eris about 557 years to complete a single orbit around the Sun. When Eris was last at this point in its orbit, the Renaissance was just getting underway in Europe. But even more extreme objects exist beyond the scattered disk. And this is where things get genuinely strange. In 2003, astronomers discovered an object called Sedna, which doesn't fit neatly into either the Kuiper Belt or the scattered disk categories. Sedna is roughly 600 miles across, large enough to qualify as a dwarf planet candidate. But what made Sedna remarkable wasn't its size, it was its orbit. Sedna never comes closer to the Sun than about 76 astronomical units. That's more than twice the distance of Neptune. And at its farthest point, Sedna swings out to about 937 astronomical units from the Sun. Its orbital period is roughly 11,400 years. The last time Sedna was at this point in its orbit, human civilization was just beginning to emerge from the Stone Age. Sedna's orbit is puzzling because it can't be easily explained by Neptune's gravity alone. Neptune is too far away to have scattered Sedna onto its current orbit. Something else must have been responsible. Astronomers have proposed several explanations. Maybe a passing star early in the solar system's history came close enough to gravitationally tug Sedna into its current orbit. Maybe the Sun formed in a dense cluster of stars where gravitational interactions were common, and one of those interactions nudged Sedna outward. Or maybe there's an undiscovered massive planet in the outer solar system, sometimes called Planet 9, whose gravity shaped Sedna's orbit along with the orbits of several other distant objects that share similar orbital characteristics. The Planet 9 hypothesis has generated enormous excitement and debate since it was proposed in 2016 by astronomers Konstantin Batygin and Mike Brown. They noticed that several distant scattered disk objects, including Sedna, had orbits that clustered together in a way that was statistically unlikely to happen by chance. They calculated that the clustering could be explained by the gravitational influence of an undiscovered planet, roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of 400 to 800 astronomical units on an elongated orbit. This hypothetical planet would be so far away and so faint that it could easily have escaped detection by existing surveys. Astronomers are actively searching for it using some of the most powerful telescopes on Earth, but as of now, Planet 9 has not been found. It remains a hypothesis, tantalizing but unproven. Whether Planet 9 exists or not, the scattered disk and objects like Sedna tell us something important. The solar system extends far beyond the Kuiper Belt. Objects orbit the Sun at distances of hundreds and even thousands of astronomical units. The space beyond Neptune is not empty. It's populated by icy bodies on orbits so elongated and so enormous that a single trip around the Sun takes thousands or tens of thousands of years. But even the scattered disk, with its extreme orbit stretching out to nearly 1,000 astronomical units, is not the farthest extent of the solar system. Beyond the scattered disk, beyond the reach of any telescope that has ever observed a solar system object directly, lies something vastly larger. We'll get there soon. But first, we need to understand something else that's happening in this region of space. Something invisible and extraordinary that defines a completely different kind of boundary. Because while the Kuiper Belt and scattered disk are defined by solid objects, by chunks of ice and rock orbiting the Sun, there's another boundary out here that has nothing to do with solid objects at all. It's defined by particles, by the flow of charged matter streaming outward from the sun at incredible speeds, and by what happens when that flow runs into the material between the stars. This boundary is invisible. You can't see it with a telescope. You can't photograph it, you can't touch it. But it's real. And 2 spacecraft that we built and launched decades ago have actually crossed it, sending back data as they pass through. This invisible boundary is one of the most important edges in the solar system, and understanding it is essential to answering the question of where our solar system truly ends. But before we explore that boundary, let's take a moment to appreciate what we've already learned about the space beyond Neptune. The Kuiper Belt and scattered disk together represent a vast reservoir of primordial material. These icy bodies are relics from the solar system's birth, preserved in the deep cold for billions of years. They carry information about the conditions that existed when the sun and planets were forming. Every time a comet falls inward from this region and becomes visible in our sky, it's delivering a message from the distant past. A sample of the original raw material from which everything in the solar system was built. These outer regions also tell us that the solar system is not a static, finished structure. It's dynamic. Objects in the Kuiper Belt and scattered disk interact gravitationally with Neptune and with each other. Orbits shift over time. Objects are scattered inward, becoming comets that visit the inner solar system, or scattered outward, drifting into the even more distant reaches of the solar system. The outer solar system is slowly evolving, reshuffling its population of icy bodies over timescales of millions and billions of years. And the outer regions tell us something else. They tell us that the solar system is vast. Not vast in the way most people imagine, with planets spread across a few billion miles, but genuinely, extraordinarily vast. The Kuiper Belt alone extends the solar system well beyond Neptune. The scattered disk pushes it out further still, to hundreds or even 1,000 astronomical units. And what lies beyond the scattered disk, what lurks in the darkness at distances so great that even light takes days or weeks or months to cross them, makes even the scattered disk seem small by comparison. The space beyond Neptune is not empty. It's not a void. It's not the edge. It's the beginning of a transition. The start of a long, gradual fade from the organized structure of the planetary system into the vastness of interstellar space. Each layer we've encountered so far, the Kuiper Belt, the scattered disk, and the strange isolated objects like Sedna on their extreme orbits, adds another chapter to this transition. The solar system doesn't end, it thins out. It becomes more sparse, more scattered, more diffuse. The objects become fewer and farther between. The sun's influence weakens, but the transition is gradual. There is no wall, no fence, no sharp line where you pass from inside to outside. And that gradual transition has another layer still to reveal. A boundary defined not by ice and rock, but by the sun's breath itself. The invisible, supersonic wind of charged particles that flows outward from our star in every direction. That wind has been blowing for 4.6 billion years, inflating a gigantic bubble in the gas between the stars. And the edge of that bubble, the place where the sun's wind finally falters and gives way to the material between the stars, is another kind of edge entirely. An edge that 2 small spacecraft, built by human hands and launched nearly 50 years ago, have already crossed. We've now traveled beyond the planets, through the frozen wilderness of the Kuiper Belt, and out into the scattered disk, where icy bodies drift on orbits so elongated They take thousands of years to complete. But all of those structures are defined by solid objects, chunks of ice and rock orbiting the sun in the darkness. Now we need to talk about something completely different. An invisible structure that fills the entire solar system, a structure you can't see, can't photograph, and can't touch, but one that defines one of the most important boundaries in all of space. To understand this structure, we need to start with the sun itself, because the sun isn't just sitting there quietly shining. It's doing something far more dramatic. It's blowing. The sun is constantly releasing a stream of charged particles, mostly protons and electrons, in every direction at once. This stream is called the solar wind, and it's been flowing outward from the sun continuously for 4.6 billion years. The solar wind isn't gentle, it's fast. Near Earth, the solar wind travels at speeds between roughly 300 and 800 kilometers per second. That's between about 670,000 and 1.8 million miles per hour. At its slowest, the solar wind is still moving fast enough to cross the distance from New York to Los Angeles in about 6 seconds. At its fastest, it covers that distance in about 3 seconds. This is an unimaginably fast river of particles streaming outward from the sun in all directions, filling the space between the planets and rushing outward into the darkness beyond. The solar wind exists because the sun's outer atmosphere, called the corona, is extraordinarily hot. The surface of the sun has a temperature of about 5,500 degrees Celsius. But the corona, the wispy, tenuous atmosphere that extends above the surface, is far hotter, reaching temperatures of 1 to 3 million degrees Celsius. This is one of the great puzzles of solar physics. The corona is hundreds of times hotter than the surface below it, and scientists are still working to understand exactly why. But whatever the cause, the extreme heat of the corona gives the particles in it so much energy that they can escape the sun's gravity entirely. They fly outward into space, carrying with them a portion of the sun's magnetic field, stretched and dragged outward like taffy being pulled across the solar system. This solar wind doesn't just disappear into nothing, it fills the space between the planets. Every cubic centimeter of space near Earth contains a few particles of solar wind, protons and electrons moving at hundreds of kilometers per second. That doesn't sound like much, and in terms of density, it isn't. The solar wind near Earth is far more tenuous than the best vacuum we can create in any laboratory on our planet. But what the solar wind lacks in density, it makes up for an extent. It fills a colossal volume of space, stretching outward from the sun in every direction, rushing past all the planets, past the Kuiper Belt, past the scattered disk, out into the distant reaches of the solar system. As the solar wind flows outward, it inflates a vast bubble in the gas that fills the space between the stars. This gas, called the interstellar medium, is extremely thin, just a few atoms per cubic centimeter on average, far thinner than any vacuum on Earth. But it's there. The space between the stars is not truly empty. It's filled with a sparse mix of hydrogen, helium, and traces of heavier elements, along with cosmic dust and magnetic fields. This interstellar gas has its own pressure, its own density, and its own motion. It's not static. The sun and the entire solar system are moving through this interstellar material at a speed of about 26 kilometers per second, roughly 58,000 miles per hour. The solar wind pushes against this interstellar medium, and the interstellar medium pushes back. The result is a huge cavity in the interstellar gas, a bubble carved out by the relentless outward pressure of the solar wind. This bubble is called the heliosphere, from the Greek word helios meaning sun and sphere for its roughly rounded shape. The heliosphere is not perfectly spherical. It's slightly compressed on the side facing the direction of the sun's motion through interstellar space, and elongated on the trailing side. Somewhat like the shape of a boat moving through water, with a blunter front and a longer wake behind. But in general terms, it's a vast bubble surrounding the entire solar system, separating the sun's domain from the interstellar environment beyond. Everything we've discussed so far, the planets, the moons, the asteroids, the Kuiper Belt, the scattered disk, all of it sits inside this bubble. The heliosphere encloses the entire planetary system and extends well beyond it. It's one of the largest structures associated with the solar system, and it defines a boundary that's fundamentally different from the orbital boundaries of planets or icy debris. The heliosphere's boundary is defined not by solid objects, but by particles and fields. It's the place where the sun's influence, in the form of its outflowing wind, gives way to the influence of the interstellar medium. But the boundary of the heliosphere isn't a single, sharp wall. It's a layered transition. A series of zones where the solar wind slows, heats up, compresses, and eventually merges with the interstellar gas. Understanding these layers is essential to understanding what it means to cross the edge of the heliosphere, and what it meant when two human-built spacecraft actually did it. The first layer is called the termination shock. As the solar wind rushes outward from the sun, it's moving at supersonic speeds, faster than the speed of sound in that medium. But as it gets farther and farther from the sun, it's pushing against more and more interstellar pressure. Eventually, at a distance of roughly 80 to 100 astronomical units from the sun, the solar wind can no longer maintain its supersonic speed. It slams into the resistance of the interstellar medium and abruptly slows down, like a car hitting a wall of thick mud. This sudden deceleration is the termination shock. At the termination shock, the solar wind drops from supersonic to subsonic speed. The particles pile up and compress, becoming denser and hotter. The kinetic energy of the fast-moving particles is converted into thermal energy, heating the solar wind to temperatures of millions of degrees. This sounds dramatic, and in a physical sense it is, but you wouldn't feel any heat if you were floating in this region, because the gas is so incredibly thin. Even at millions of degrees, there are so few particles per cubic centimeter that the total amount of thermal energy in any given volume is tiny. You'd freeze to death long before any hot particle touched you. But in terms of the physics of the particles themselves, the termination shock is a genuine shockwave, a place where the solar wind's properties change abruptly and dramatically. Beyond the termination shock, the solar wind continues to flow outward, but now it's moving slowly, subsonically, and it's being deflected and compressed by the interstellar medium pressing in from outside. This region between the termination shock and the outer boundary of the heliosphere is called the Helios Heath. Think of it as a thick, turbulent buffer zone. The solar wind particles in the Helios sheath are hot, dense compared to the solar wind upstream, and disordered. They're no longer flowing outward in an organized stream. Instead, they're swirling and tumbling, pushed and squeezed by the external pressure of interstellar space. The Helios sheath is roughly 30 to 50 astronomical units thick, though its exact thickness varies depending on the direction you're traveling and the conditions in the interstellar medium. It's a vast, turbulent region filled with compressed solar wind material, and crossing it takes years even at the speeds of our fastest spacecraft. This is a region where two very different environments, the solar wind and the interstellar medium, are fighting for dominance. The solar wind is trying to push outward. The interstellar medium is pushing inward. The heliosheath is where this battle takes place, and neither side has a clear advantage. Finally, at the outer edge of the heliosheath, we reach the heliopause. This is the actual boundary of the heliosphere. The surface where the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium. At the heliopause, solar wind particles stop moving outward. They can't push any farther against the resistance of the interstellar gas. Beyond this point, the dominant particles in space are no longer from the sun. They're from the stars. They're interstellar particles, hydrogen and helium atoms from the galaxy itself, carried by the interstellar wind and permeated by the galaxy's magnetic field. The heliopause sits at roughly 120 to 140 astronomical units from the Sun, depending on the direction and the conditions. That's about 3 times the distance from the Sun to Neptune. It's about 11 billion miles from the Sun. Light from the Sun takes roughly 17 hours to reach the heliopause. It's incredibly far away by any human standard, and yet, in the context of the full solar system, it's still relatively close. The gravitational boundary of the solar system, the outer edge of the Oort Cloud, extends to roughly 100,000 astronomical units. The heliopause at 120 astronomical units is barely past the front door. Now here's what makes all of this more than just theoretical physics. 2 spacecraft that we built, launched, and guided across billions of miles of space have actually crossed these boundaries. They've sent back data from the heliosheath and from beyond the heliopause. They've told us what it's actually like out there, not what we theorized or modeled, but what the measurements show. These spacecraft are Voyager 1 and Voyager 2, and their journeys through the outer solar system represent one of the greatest achievements in the history of exploration. Voyager 1 and Voyager 2 were launched in 1977, just 16 days apart. Their primary missions were to study Jupiter and Saturn, which they did spectacularly, sending back images and data that revolutionized our understanding of those giant planets and their moons. Voyager 2 went on to visit Uranus in 1986 and Neptune in 1989, making it the only spacecraft ever to visit those ice giants. But after their planetary encounters, the Voyagers kept going. There was no way to stop them and no reason to. They were moving fast enough to escape the sun's gravity entirely, so they continued outward, flying through the darkness of the outer solar system at speeds of roughly 35,000 to 38,000 miles per hour. They carried instruments that could measure the properties of the solar wind, the magnetic field, and the charged particles in their environment. And as they traveled farther and farther from the sun, those instruments began to detect changes that scientists had predicted but never before measured directly. Voyager 1 crossed the termination shock in December of 2004 at a distance of about 94 astronomical units from the Sun. The instruments on board detected a dramatic change in the solar wind. The speed of the particles dropped sharply. The magnetic field became stronger and more turbulent. The temperature of the plasma increased. Everything was consistent with what scientists expected at the termination shock. The spacecraft had entered the heliosheath. Voyager 2 crossed the termination shock in August of 2007, at a distance of about 84 astronomical units. Interestingly, it crossed at a shorter distance than Voyager 1, which told scientists that the heliosphere is not symmetric. It's slightly compressed on some sides and extended on others, flexing and breathing in response to changes in the solar wind and the interstellar medium. The heliosphere is not a rigid shell. It's a dynamic, living structure that pulsates and shifts over time. Both spacecraft then spent years traversing the heliosheath, measuring conditions in this turbulent buffer zone between the solar wind and interstellar space. The data they sent back revealed a region more complex and chaotic than anyone had expected. The magnetic field in the heliosheath was bubbly, filled with magnetic structures that some scientists compared to foam. The direction of the magnetic field flipped back and forth over short distances, creating a frothy, disordered environment, nothing like the relatively smooth, organized solar wind closer to the sun. Then came the historic crossings. On August the 25th, 2012, Voyager 1 crossed the heliopause and entered interstellar space. It was about 122 astronomical units from the Sun. The crossing was detected by a sudden and dramatic change in the particles surrounding the spacecraft. The density of solar wind particles dropped by a factor of more than 1,000. Simultaneously, the density of galactic cosmic rays, high-energy particles from outside the solar system, increased sharply. The spacecraft had left the Sun's domain and entered the space between the stars. But the crossing wasn't quite as clean as you might expect. Scientists had predicted that when Voyager 1 crossed the heliopause, the direction of the magnetic field would change dramatically, rotating to align with the interstellar magnetic field rather than the Sun's field. But the magnetic field direction didn't change as much as expected. This created confusion. For months, scientists debated whether Voyager 1 had actually crossed the heliopause or entered some previously unknown transitional region. It wasn't until they analyzed data from a solar eruption that sent a wave of particles rippling outward through the heliosphere that they could confirm the crossing. The wave reached Voyager 1's position and caused the surrounding plasma to vibrate. By measuring the frequency of those vibrations, scientists could determine the density of the plasma, and the density confirmed that Voyager 1 was in interstellar space. Voyager 2 crossed the heliopause on November 5th, 2018, at a distance of about 119 astronomical units. Unlike Voyager 1, Voyager 2 still had a working plasma science instrument, which allowed it to make direct measurements of the plasma as it crossed the boundary. These measurements confirmed what Voyager 1's data had suggested. The heliopause is a real, detectable boundary. On one side, the plasma is dominated by particles from the Sun moving outward. On the other side, the plasma is dominated by particles from the interstellar medium. The transition is relatively sharp, occurring over a distance of just a few astronomical units, maybe less. It's not a gradual fade, but a genuine boundary, a place where one environment gives way to another over a comparatively short distance. So by 2018, both Voyager spacecraft had crossed the heliopause and entered interstellar space. This was a monumental achievement. For the first time in history, human-made objects were traveling through the space between the stars, sending back data about an environment that no instrument had ever directly measured before. The data confirmed many predictions, but also raised new questions. The magnetic field direction didn't change as expected at the heliopause. The boundary was sharper in some ways and more gradual in others than models had predicted. The interstellar medium just beyond the heliopause turned out to be slightly denser and more structured than expected. But here's the critical point. The thing that most people misunderstand about the Voyager crossings. When scientists announced that Voyager 1 had entered interstellar space, many people interpreted that as meaning Voyager had left the solar system. Headlines around the world proclaimed that Voyager had exited the solar system. But that's not accurate. The Voyagers crossed the heliopause, which is the boundary of the heliosphere, the bubble of solar wind surrounding the sun. But the heliosphere is not the same thing as the solar system. The solar system extends far beyond the heliosphere. The sun's gravitational influence, which is what ultimately defines the solar system, reaches much, much farther than the solar wind. The heliopause is at about 120 astronomical units. The sun's gravitational dominance extends to roughly 100,000 astronomical units. The Voyagers have barely begun to leave the solar system in gravitational terms. They're in interstellar space from the standpoint of particles and plasma. The wind around them is interstellar wind, not solar wind. But gravitationally, they are still firmly bound to the sun's domain. They are still orbiting the sun. They will continue to orbit the sun for a very, very long time. Their trajectories slowly shaped by the sun's grip across distances that dwarf anything they have traveled so far. This distinction is one of the most important and most commonly misunderstood aspects of the solar system's edge. The heliosphere defines one kind of boundary, a particle boundary, a plasma boundary. Cross it, and the dominant particles around you change from solar to interstellar. That's significant and meaningful, but it's not the only boundary, and it's not the outermost boundary. The gravitational boundary is much farther away, and beyond the gravitational boundary, the solar system truly gives way to the wider galaxy. Let's pause for a moment and think about what the heliosphere means in practical terms, because it does more than just define a boundary. The heliosphere is a shield. It protects everything inside it, including Earth, from the full intensity of galactic cosmic rays. These are high-energy particles, mostly protons, that come from outside the solar system. They're produced by supernova explosions, by the turbulent environments around black holes, and by other violent events in the galaxy. They travel through interstellar space at close to the speed of light, carrying enormous amounts of energy. Without the heliosphere, Earth's surface would be bombarded by significantly more cosmic rays than it currently receives. The heliosphere's magnetic field deflects and slows many of these particles, reducing the cosmic ray flux inside the bubble compared to outside. This is called solar modulation. When the sun is at the peak of its 11-year activity cycle, the solar wind is stronger and the heliosphere provides more protection. When the sun is at its quietest, the protection weakens and more cosmic rays penetrate to the inner solar system. Cosmic rays are not just a curiosity. They interact with Earth's atmosphere, producing cascades of secondary particles that reach the ground. They contribute to background radiation. They can damage DNA and increase cancer risk, which is a concern for astronauts and a major challenge for any future crewed missions beyond Earth's magnetic field. The heliosphere provides a first layer of defense against these particles, with Earth's own magnetic field and atmosphere providing additional layers. The heliosphere also interacts with the interstellar medium in ways that affect the solar system's long-term evolution. As the sun moves through the galaxy, it encounters regions of interstellar space with different densities and compositions. When the sun passes through a denser region of interstellar gas, the heliosphere gets compressed. A smaller heliosphere means less protection from cosmic rays. Some scientists have speculated that episodes of increased cosmic ray flux caused by a compressed heliosphere might have contributed to climate changes or even mass extinction events on Earth over geological timescales, though this remains a topic of active debate and research. The heliosphere is also not permanent. It exists only as long as the sun produces a solar wind. When the sun eventually dies, roughly 5 billion years from now, the solar wind will cease. The heliosphere will dissipate, and the space currently enclosed within it will be flooded with interstellar gas and cosmic rays. The bubble will pop, so to speak, and the sun's remnant, a slowly cooling white dwarf, will sit exposed to the full interstellar environment with no protective shell of outflowing particles around it. Now, there's one more thing about the heliosphere that's worth understanding, and it has to do with its shape. I mentioned earlier that the heliosphere is somewhat compressed on the side facing the sun's direction of travel and elongated on the trailing side. But the exact shape is a matter of ongoing scientific debate. For decades, the standard model depicted the heliosphere as having a long, comet-like tail stretching behind it, called the heliotail, extending perhaps hundreds or thousands of astronomical units downstream from the sun. Under this model, the overall heliosphere resembles a windsock or a jellyfish, streaming its extended tail through the interstellar medium. But more recent research has challenged this picture. Some models based on data from the Voyager spacecraft and from other missions like the Interstellar Boundary Explorer, or IBEX, which is a satellite in Earth orbit that detects particles coming from the heliosphere's boundary, suggest the heliosphere might be more rounded than previously thought. Some models even propose a shape more like a croissant or a deflated ball, without a long tail at all. The debate is ongoing, and the shape of the heliosphere remains one of the major open questions in heliophysics. What matters for our story is that the heliosphere, whatever its exact shape, defines a real and important boundary. Inside the heliosphere, you're in the sun's domain. The particles around you come from the sun. The magnetic field is the sun's field, carried outward by the solar wind. Outside the heliosphere, you're in interstellar space. The particles come from other stars, from supernova remnants, from the diffuse gas that fills the galaxy. The magnetic field is the galactic magnetic field, shaped by forces and events far beyond the solar system. This is a profound boundary. It separates the local from the cosmic. Inside the heliosphere, conditions are shaped primarily by the sun. The sun's output determines the temperature, the particle density, the magnetic field strength, and the level of cosmic ray protection. Outside the heliosphere, conditions are determined by the galaxy, by the collective influence of billions of stars, by the supernova remnants and giant molecular clouds, and the slow rotation of the Milky Way itself. Crossing the heliopause means leaving the sun's immediate influence and entering a much larger, much older, much more vast environment. But as we've established, crossing the heliopause does not mean leaving the solar system. The Voyager spacecraft are in interstellar space from a plasma perspective, but they're still well within the sun's gravitational territory. They're still orbiting the sun, and they will continue to do so for an extremely long time, because the sun's gravity reaches far beyond the heliopause, far beyond anything the Voyagers have encountered, out to distances so vast that they challenge our ability to comprehend them. The heliosphere's boundary at roughly 120 astronomical units is just one layer in the solar system's complex multi-layered edge. Beyond it, the solar wind gives way to interstellar particles, but the sun's gravity continues to hold sway. And in that gravitational domain, in the cold darkness beyond the heliosphere, there exists a structure so large, so diffuse, and so mysterious that it dwarfs everything we've discussed so far. A structure that has never been directly observed by any telescope or spacecraft. A structure we know exists only because of the icy visitors it occasionally sends plunging into the inner solar system. A structure that stretches nearly halfway to the next star, marking the true outermost reaches of the sun's domain. That structure is the Oort Cloud. And it's where we're going next. We've now traveled an extraordinary distance from home. We've crossed the planetary region, passed through the frozen debris fields of the Kuiper Belt and the scattered disk, and followed two tiny spacecraft as they punch through the invisible boundary where the sun's breath finally gives way to the wind between the stars. The heliosphere is behind us. The solar wind no longer reaches this far. Out here, the particles drifting through space come not from the sun, but from distant stars, from supernova remnants, from the diffuse gas that permeates the Milky Way. By the standards of particle physics, we're already in interstellar space. But by the standards of gravity, we haven't even come close to leaving the solar system. Because the sun's gravitational reach extends far, far beyond the heliopause. And in that vast gravitational territory, stretching outward for tens of thousands of astronomical units, there exists the largest, most mysterious, and most poorly understood structure in the entire solar system. A structure so enormous that everything we've talked about so far, the planets, the Kuiper Belt, the scattered disk, the heliosphere, all of it fits inside its innermost boundary like a marble sitting at the center of a cathedral. This structure is the Oort Cloud. And to understand why scientists believe it exists, we need to talk about comets. Not the short period comets that swing through the inner solar system every few years or decades, like Halley's Comet with its roughly 76-year orbit. Those comets come from the Kuiper Belt and the scattered disk. Their orbits are confined to the general plane of the solar system, and their periods, while sometimes long by human standards, are manageable by astronomical standards. We're talking instead about a different kind of comet entirely. Long period comets. These are comets that arrive in the inner solar system on orbits so elongated and so vast that they take thousands, tens of thousands, or even millions of years to complete a single trip around the sun. Some of them have never been observed before in all of recorded human history. They appear in our sky once, blazing briefly as solar heat ignites their ancient ices into luminous tails, before arcing away on trajectories that won't bring them back for millennia. What makes long-period comets so important for understanding the solar system's outer reaches is where they come from. When astronomers trace these comets' orbits backward, calculating where they've been before they fell inward toward the sun, they find that these comets arrive from every direction. Not just from the plane of the solar system, where the planets and the Kuiper Belt orbit, but from above, below, and from every angle in between. Their orbits are randomly oriented, distributed across the entire sky without any preference for the ecliptic plane. This tells us something crucial. Whatever reservoir these comets come from, it's not a flat ring or belt like the Kuiper Belt. It's spherical. It surrounds the solar system in every direction, forming a shell rather than a disk. This was the key insight that led Jan Oort, the Dutch astronomer, to propose the existence of the cloud that now bears his name. In 1950, Oort analysed the orbits of long-period comets and noticed two things. First, their orbits were randomly oriented, indicating a spherical source. Second, many of them had orbits suggesting they came from distances of roughly 20,000 to 100,000 astronomical units from the Sun. Based on these observations, Oort proposed that a vast, roughly spherical cloud of icy bodies surrounds the solar system at enormous distances, extending from perhaps 2,000 astronomical units out to 100,000 astronomical units, or even beyond. Let me try to convey the scale we're talking about here because the numbers are genuinely staggering. 100,000 astronomical units is about 1.6 light years. The nearest star, Proxima Centauri, is about 4.24 light years away. So the outer edge of the Oort cloud, if it extends to 100,000 astronomical units, reaches nearly half the way to the nearest star. If the distance from the Sun to Neptune were the length of your arm, the Oort cloud's outer boundary would be over a mile away. If the distance from the Sun to Neptune were the length of your arm, the Oort cloud's outer boundary would be over a mile away. The inner boundary of the Oort cloud is thought to begin at roughly 2,000 to 5,000 astronomical units from the Sun. This inner region, sometimes called the Hills cloud, after astronomer Jack Hills, who studied it extensively, is believed to be denser and more disk-shaped than the outer Oort cloud. It may contain significantly more objects than the outer cloud, but because it's closer to the Sun and more gravitationally bound, its members are less easily dislodged and less likely to fall inward as visible comets. The outer Oort cloud, from roughly 20,000 to 100,000 astronomical units, is more spherical and more loosely bound. Objects here are barely held by the Sun's gravity. They orbit so slowly and so far away that the slightest gravitational nudge can alter their paths dramatically. How many objects are in the Oort cloud? No one knows for certain because we've never directly observed a single one. These objects are small, typically a few miles across, and they're incredibly far away. An object a few miles in diameter at 50,000 astronomical units from the Sun reflects so little sunlight that no existing telescope could detect it. We infer the Oort cloud's existence entirely from the comets it sends our way. Based on the rate at which long-period comets arrive in the inner solar system, and on models of how those comets are perturbed out of the cloud, astronomers estimate the Oort cloud contains somewhere between several hundred billion and perhaps 2 trillion icy objects larger than about half a mile across. Some estimates go even higher. The total mass of the Oort cloud is uncertain, but is probably somewhere between 1 and 40 times the mass of Earth, with most estimates clustering around a few Earth masses. Think about what that means. A spherical shell of trillions of icy bodies, stretching from a few thousand astronomical units to 100,000 astronomical units from the Sun, containing several times the mass of Earth in frozen material. And we've never seen a single one of these objects directly. We know they're there only because every few years or decades, one of them gets dislodged from its distant orbit and comes tumbling inward, appearing in our sky as a comet before disappearing back into the darkness. The objects in the Oort cloud are believed to be similar in composition to Kuiper Belt objects. Mixtures of water ice, frozen methane, frozen ammonia, frozen carbon dioxide, and rocky dust. They're formed from the same primordial substances that gave rise to the planets. Locked in ultra-cold suspension at the outer solar system's distant frontier for 4.6 billion years. But they didn't form where they are now. The Oort Cloud is too far from the Sun for significant amounts of material to have existed in the original solar nebula at those distances. Instead, Oort Cloud objects are thought to have formed much closer to the Sun, in the region of the giant planets, and were then gravitationally scattered outward by encounters with Jupiter, Saturn, Uranus, and Neptune during the chaotic early history of the solar system. In the first few 100 million years after the solar system formed, the giant planets were rearranging themselves, migrating through the solar system, their orbits shifting and changing. During this period, the gravitational influence of the giant planets was like a cosmic catapult, flinging small icy bodies in every direction. Some were flung into the Sun, some were ejected from the solar system entirely, becoming rogue objects drifting through interstellar space. But some were flung outward to distances of thousands or tens of thousands of astronomical units, where the gentle gravitational influence of passing stars and the overall gravitational tide of the Milky Way galaxy gradually circularized their orbits, trapping them in the vast shell we now call the Oort Cloud. This formation mechanism means the Oort Cloud is not a primordial structure that has existed since the solar system's birth. It's a secondary structure, assembled over millions of years through gravitational interactions. The objects in it are primordial. They date from the solar system's formation, but their current location is the result of a long and violent history of gravitational scattering. They're exiles, cast out from the inner solar system by the giant planets and captured into distant orbits by the gentle hands of passing stars and the galaxy itself. The Oort Cloud is not static. It's constantly being reshaped by external gravitational influences. Passing stars are the most important of these. The Sun, like all stars, is moving through the galaxy. Over millions of years, other stars occasionally pass relatively close to the solar system. When a star passes within a light year or two of the Sun, its gravity can perturb Oort Cloud objects, nudging them onto new orbits. Some are pushed outward, eventually escaping the Sun's gravity entirely and drifting away into interstellar space. Others are pushed inward, onto elongated orbits that carry them into the inner solar system, where they become visible as long-period comets. The Milky Way's galactic tide also plays a role. The gravitational pull of the galaxy as a whole, the combined gravity of all the stars, gas, and dark matter in the Milky Way, creates a tidal force that continuously pulls on the most distant Oort Cloud objects. This tidal force is extremely weak, but it acts continuously over millions of years, slowly changing the orbits of distant icy bodies. Over time, the galactic tide can shift objects from circular orbits in the outer Oort Cloud to elongated orbits that plunge inward toward the Sun. Together, passing stars and the galactic tide are the mechanisms that feed comets from the Oort Cloud into the inner solar system. Without these external influences, the Oort Cloud would just sit there, a silent, frozen shell of trillions of objects orbiting the Sun in the darkness, never interacting with the inner solar system at all. We'd never know it existed. It's only because external gravity occasionally dislodges members of the cloud and sends them falling inward that we see them as comets, and can infer the cloud's existence. Some of the most spectacular comets in history are thought to have originated in the Oort Cloud. Comet Hale-Bopp, which was visible to the naked eye for a record 18 months in 1996, and 1997, is now on an orbit of roughly 2,520 years. But before gravitational interactions with Jupiter shortened its path during that visit, its previous orbital period was about 4,200 years, meaning its prior passage through the inner solar system occurred around 2200 BCE, when the Great Pyramids of Egypt were still relatively new. Before that visit, its orbit was even longer, and gravitational interactions during its passage through the inner solar system shortened it. Comet Hyakutake, which made a spectacular appearance in 1996, is now on an orbit of roughly 70,000 years after gravitational interactions during its recent passage dramatically extended its path. Before that change, its orbital period was about 17,000 years, placing its previous visit to the inner solar system during the last ice age, when mammoths still roamed much of the northern hemisphere. These comets carry material from the Oort Cloud, ices and dust from a region so distant and so cold that nothing has disturbed them since the solar system's earliest days. When they approach the sun and their ices begin to vaporize, they release gas and dust that scientists can analyze. Each comet becomes a natural laboratory, delivering samples from the outermost frontier directly into our instruments. The material they release tells us about the chemical composition, temperature, and conditions of the solar nebula 4.6 billion years ago. Every comet from the Oort Cloud is a messenger from both the distant past and the distant reaches of the solar system, carrying information about conditions in both time and space that we could never access directly. Now, let's talk about the gravitational boundary itself, because the Oort Cloud's outer edge is defined by something fundamental. It's defined by the point where the sun's gravitational pull becomes too weak to hold onto objects. This is a concept called the heliosphere, the region around an astronomical body within which its gravity dominates over the gravity of other nearby bodies. For the sun, the relevant competition is with the gravity of nearby stars and the overall gravitational field of the Milky Way galaxy. The sun's heliosphere, the region within which its gravity is stronger than the competing gravitational influences, has a radius of roughly 1 to 2 light years, or about 60,000 to 125,000 astronomical units. Beyond this distance, the sun simply can't hold onto objects anymore. The gravitational pull of passing stars and the tidal force of the galaxy are stronger than the sun's grip. Any object beyond the heliosphere would drift away, captured by some other gravitational influence, or becoming a free-floating object in interstellar space. This gravitational boundary is the true outermost edge of the solar system. If we define the solar system as the region dominated by the sun's gravity, it's not a sharp line, of course. Gravity doesn't have a wall. It fades gradually with distance, following the inverse square law. At the outer edge of the heliosphere, the sun's gravity is incredibly weak, just barely stronger than the competing forces. Objects in this region are loosely bound at best, held by the thinnest gravitational thread. A minor perturbation, a distant star passing within a few light years, a slight change in the galactic tidal force could snap that thread and release the object into interstellar space. And this brings us to the crucial realization that ties everything together. The solar system doesn't have one edge. It has many edges, each defined by a different physical process, each occurring at a vastly different distance from the sun. The first edge is the planetary boundary at about 30 astronomical units. This is where the last planet, Neptune, orbits. Beyond this point, there are no more major planets, no more large gravitationally dominant worlds sweeping up debris and shaping the structure of their surroundings. This is the edge that most people think of when they imagine the solar system, and it's real, but it's just the innermost boundary. The second edge is the Kuiper Belt's outer boundary at roughly 50 astronomical units. Beyond this distance, the classical belt of icy objects thins out dramatically. Objects still exist beyond 50 astronomical units, scattered disk members on their elongated orbits, but the dense ring of debris that characterizes the classical Kuiper Belt ends here. The third edge is the heliopause at roughly 120 astronomical units. This is where the solar wind gives way to the interstellar medium. Beyond this point, the particles surrounding you come from the galaxy rather than the sun. This is the boundary that the Voyager spacecraft crossed, and it's the edge that most scientists refer to when they talk about entering interstellar space. The fourth edge, the outermost one, is the gravitational boundary at roughly 100,000 astronomical units, roughly 1.6 light years. This is the outer edge of the Oort Cloud, the limit of the sun's gravitational dominance, the point beyond which the sun can no longer hold onto material. Beyond this distance, you're truly outside the solar system in every sense. You're beyond the sun's particles, beyond its debris, and beyond its gravitational reach. These four edges span a range from 30 astronomical units to 100,000 astronomical units. The outermost edge is more than 3,000 times farther from the sun than the innermost edge. If you drew a map of the solar system that showed all four edges at the correct scale, the planetary region would be an invisible dot at the center. The Kuiper Belt would be a slightly larger but still tiny dot. The heliopause would be a small circle, and the Oort Cloud would fill the rest of the page. The vast majority of the solar system's volume is occupied by that distant spherical reservoir, a structure so diffuse and so remote that remains in many ways a theoretical framework built on indirect evidence. This layered structure means the transition from the solar system to interstellar space is not a sudden event but a gradual process that unfolds over an enormous range of distances. If you were traveling outward from the sun, you'd pass through the planetary system in the first 30 astronomical units. You'd cross through the Kuiper Belt and scatter disk over the next few hundred astronomical units. You'd punch through the heliopause at about 120 astronomical units, leaving the solar wind behind, and then you'd spend the next 100,000 astronomical units slowly crossing the Oort Cloud, moving through an increasingly sparse population of icy bodies, each one more loosely bound to the sun than the last, until finally you reach the point where the sun's gravity could no longer hold onto anything at all. At that point, you would have left the solar system, but you wouldn't notice any dramatic change. Nothing would mark the moment of passage. The stars around you would look the same. The darkness would be just as dark. The silence just as silent. The only difference would be in the mathematics of gravity. Behind you, objects orbit the sun. Ahead of you, they don't. The transition is invisible, mathematical, and profound. Voyager 1 is currently about 165 astronomical units from the sun, and Voyager 2 is at roughly 139 astronomical units. Both have crossed the heliopause, but they're nowhere near the Oort Cloud, assuming it begins at roughly 2,000 astronomical units. They haven't even reached the inner edge of the Oort Cloud yet. They're in the gap between the heliopause and the Oort Cloud's inner boundary, a region sometimes called the heliospheric boundary layer or simply the very local interstellar medium. At their current speed of roughly 35,000 miles per hour, the Voyagers would take about 500 years to reach the inner edge of the Oort Cloud at 2,000 astronomical units, and roughly 30,000 years to reach the outer edge at 100,000 astronomical units. They would need about 73,000 years to reach the distance of Proxima Centauri, though neither spacecraft is aimed in that direction. By the time the Voyagers reach the outer edge of the Oort Cloud, their nuclear power sources will have long since died. They'll be silent, dark, frozen spacecraft drifting through the void, carrying golden records etched with sounds and images of Earth, messages from a civilization that built them and launched them, and then watched them disappear into the darkness. They'll be among the longest-lasting artifacts humanity has ever created, drifting through interstellar space for millions or billions of years, long after the civilizations that built them have changed beyond recognition or ceased to exist entirely. So, what does all of this mean? What does it mean that the solar system doesn't have a single edge, but rather a series of nested boundaries, each one defining a different kind of transition from the sun's domain to the galaxy beyond? It means that the solar system is far larger and far more complex than the simple planetary picture suggests. The textbook image of 8 planets orbiting the sun captures only the innermost fraction of 1% of the solar system's true extent. Beyond the planets lies a vast, layered structure of icy debris, solar wind, and gravitationally bound material that extends for nearly 2 light years in every direction. The solar system isn't a compact, well-defined thing with a clear edge. It's a sprawling, diffuse structure that gradually fades into the interstellar environment, like a fog thinning at its edges. It also means that the question, where does the solar system end, is not a simple question with a simple answer. It depends on what you mean by end. If you mean where the planets stop, the answer is 30 astronomical units. If you mean where the solar wind stops, the answer is about 120 astronomical units. If you mean where the sun's debris field stops, the answer is roughly 100,000 astronomical units. Each answer is correct, and each tells us something different about what the solar system is and how it interacts with the galaxy around it. And it means something else, something perhaps more profound. The solar system is not isolated. It's connected to the galaxy. The Oort Cloud's outer reaches are constantly being reshaped by passing stars and galactic tides. The heliosphere's size and shape are determined by the properties of the interstellar medium the Sun is currently moving through. The comets that occasionally visit the inner solar system are messengers from the outermost reaches, dislodged by gravitational influences that originate far beyond the Sun's control. The solar system is embedded in the galaxy, influenced by it, shaped by it, and gradually blending into it at its outermost edges. When you look up at the night sky and see the sun's light reflected off the planets, you're seeing the innermost core of an enormous structure. Beyond those familiar worlds lies a frozen belt of debris left over from the solar system's birth. Beyond that lies an invisible bubble of solar wind, a protective shell inflated by the sun's relentless outward breath. Beyond that lies a vast, spherical cloud of trillions of icy fragments, barely held by the sun's weakening gravity, stretching nearly halfway to the next star. And beyond that, the sun's influence finally fades, giving way to the great darkness between the stars, the interstellar medium, the space that connects one stellar system to the next. And this layered fading gives us something remarkable to contemplate. The sun's dominance weakens in stages, with each structure representing a different kind of authority the sun once held and slowly relinquishes. First its planets, then its debris, then its wind. And finally, at the outermost reach, its gravity. Each layer releases its grip at its own distance, creating not a single frontier but a long chain of farewells. And perhaps that's the most beautiful thing about it. The solar system doesn't stop sharply, because gravity doesn't stop sharply. The sun's pull reaches outward in every direction, getting weaker and weaker, but never quite reaching zero. In theory, every object in the universe feels the sun's gravity, however faintly. The sun's gravitational influence extends to infinity, diminishing with distance but never truly disappearing. The solar system's edge, then, is not where the sun's gravity ends, because it never truly ends. It's where other gravitational influences become stronger, where the sun is no longer the dominant force, where objects stop orbiting our star and begin responding to the wider galaxy instead. This is a fitting metaphor for our place in the cosmos. We are part of something larger. The solar system is part of the galaxy. The galaxy is part of a cluster. The cluster is part of a supercluster. At every scale, structures blend into larger structures, boundaries dissolve into transitions, and edges become gradients rather than lines. Nothing in the universe is truly isolated. Everything is connected, everything is part of something bigger, and every boundary, when you look closely enough, turns out to be a transition rather than a wall. The next time someone asks you where the solar system ends, you can tell them the truth. It doesn't end in one place. It fades outward through layers, from the familiar warmth of the planets to the frozen debris of the Kuiper Belt, through the invisible boundary of the heliosphere, into the vast and silent reaches of the Oort Cloud, and finally, at distances measured in light years rather than astronomical units, into the space between the stars. The solar system is not a thing with an edge. It's a process, a transition, a gradual fading from here to everywhere else, and that makes it more fascinating, more complex, and more beautiful than any simple diagram could ever show. So the next time you look up at the sky on a clear night, remember what you now know. The planets you can see, Mercury, Venus, Mars, Jupiter, Saturn, those are just the beginning. Beyond them stretches a solar system so vast that light itself takes nearly 2 years to cross it. A system filled with trillions of frozen worlds, invisible boundaries, and structures so large they bridge the gap between stars. You live not at the edge of a small, tidy planetary system, but at the warm center of an enormous, layered, slowly dissolving structure that reaches outward in every direction, fading gradually into the galaxy around it. The solar system is far bigger than you were taught, far stranger than you imagined, and far more connected to the universe beyond it than most people ever realize. There is no edge. There is only the long, slow, beautiful fade from home into everything else. And out there, in the cold and the dark, at distances so great they challenge our ability to comprehend them. The sun's faintest gravitational whisper still holds on, still gathers its most distant children into orbit, still defines the outermost boundary of the place we call home. Thank you for joining me on this journey to the edges of the solar system and beyond. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep explorations of the cosmos. And remember, The next time you see a comet streaking across the sky, that tiny visitor traveled from the outermost reaches of the solar system, from a place so distant that the sun is just another star in its sky. It fell inward across billions of miles of space, carrying ices that have been frozen since the earliest days of the solar system, to blaze briefly in our atmosphere before disappearing back into the darkness. That comet is a direct emissary from the true edge of the solar system, a place far beyond the planets, far beyond the solar wind, far beyond anything most people ever imagine when they picture our little corner of the universe. The solar system is vast, its edges are layered, and its story, stretching outward from the sun through structure after structure until gravity itself finally lets go, is one of the most extraordinary stories in all of science. Good night.